In the earliest chapters of human understanding, long before equations or experiments gave order to the chaos of nature, there existed a profound mystery that surrounded the forces of the world. Lightning would tear across the heavens, splitting the dark clouds with blinding light and a roar that shook the earth. People watched in awe, believing such power belonged only to gods. In ancient temples and humble homes, they rubbed amber with fur, watching tiny bits of straw leap, as if possessed by invisible spirits. No one could explain what was happening. Yet something deep within humanity's curiosity whispered that these were not acts of magic, but signs of an unseen order. For centuries, the world saw electricity, magnetism, and light as separate wonders, each isolated, each carrying its own enigma. The compass needle that pointed north seemed to obey a hidden command from the earth itself. The spark that jumped from one object to another seemed to carry life's own essence. And light, radiant and ethereal, was the very soul of existence, illuminating the path of humanity, but never revealing its own secret. Philosophers debated its nature. Was light made of particles, or was it a wave rippling through some invisible ether? No one knew, and for hundreds of years, these mysteries remained apart, scattered fragments of a larger truth waiting to be discovered. It was in the hands of early experimenters that these phenomena began to take form. When William Gilbert, the court physician of Queen Elizabeth I, began studying the strange force of magnetism, he noticed that it behaved differently from any other known interaction. It did not depend on visible contact, yet it could move objects, align metals, and influence direction itself. He called this new force electrica, from the Greek word for amber, electron. His work laid the first foundation of what would become the science of electromagnetism, though at the time, its true depth was unimaginable. Meanwhile, others like Benjamin Franklin explored electricity through bold and sometimes dangerous experiments. Franklin's kite, flying high beneath a storm cloud, became an instrument of revelation. When lightning struck and the spark leapt to his key, he proved that the heaven's fury and the small electric sparks in laboratories were born of the same essence. Yet still, no one could connect this electric fire with magnetism or light. Each stood alone, a separate mystery in nature's grand puzzle. Light, in particular, fascinated humanity since the dawn of thought. Ancient philosophers like Empedocles and Aristotle proposed that light traveled in straight lines but differed in nature from all other forces. Even Newton, centuries later, described light as a stream of tiny particles, corpuscles, each obeying precise laws of reflection and refraction. His vision of optics gave science new language and accuracy, but it also deepened the division between light and the other forces. Electricity and magnetism were physical, they moved metals and created sparks. Light was intangible, graceful, divine. Then, across the centuries, new experiments began to hint that perhaps these mysteries were not as separate as they seemed. In the late 18th century, Italian scientist Luigi Galvani discovered that electricity could cause a dead frog's legs to twitch, a phenomenon that suggested a link between electricity and life itself. His rival, Alessandro Volta, saw the effect differently and invented the first true battery, providing a steady source of electrical current. The spark of discovery was growing brighter, but still the connection to magnetism and light remained hidden in the shadows. It was Hans Christian Ørsted who first glimpsed the bridge between these worlds. In 1820, while lecturing to his students in Copenhagen, he noticed that a magnetic needle moved when placed near a current-carrying wire. The realization was staggering. Electricity could influence magnetism. Two forces that had long stood apart were now seen as intimately linked. The invisible line between them had been crossed. Ørsted's observation spread across Europe like wildfire. It was as if a curtain had been lifted from the face of nature. Soon after, André Marie Ampère, inspired by Ørsted's discovery, formulated mathematical laws to describe how electric currents produce magnetic fields. Michael Faraday, an Englishman of humble origin, took the next great leap by demonstrating that the reverse was also true. that moving magnets could generate electricity. The unity between electricity and magnetism was no longer speculation, it was a measurable, demonstrable truth. Yet still, light stood apart, a celestial wanderer whose true nature had not yet been bound to these earthly forces. Faraday's experiments revealed something profound: invisible lines of force surrounding magnets and conductors. To him, these lines were not mere abstractions but physical realities, the living architecture of the universe. He imagined space itself filled with fields of energy, constantly in motion, invisible but powerful. His vision was intuitive and pictorial, not mathematical. He lacked the formal tools to express these ideas in equations, but his mind saw the unseen. In his notebooks, he drew loops and waves, showing how energy might propagate through space. He was painting the early outlines of what would later be called the electromagnetic field. For the scientists of the early 19th century, the challenge was not only to discover new phenomena, but to find order within them. Experiments multiplied, theories clashed, and nature's secrets seemed both closer and more complex than ever. Yet within this storm of discovery, one pattern was beginning to emerge: a sense that all these forces were not strangers to each other, but parts of a greater unity waiting to be revealed. Imagine the 1800s, a world lit by candles, where communication traveled no faster than a horse could ride. The idea that invisible forces could one day carry voices, images, and energy across continents would have seemed unthinkable. But the seeds of that revolution were already sprouting in the laboratories of Europe. Scientists like Faraday and Ampere were shaping a new understanding of force, one that would soon merge with the mystery of light itself. Light had long resisted comprehension. Isaac Newton's particle theory of light had dominated scientific thought for generations. But Thomas Young and Augustine, John Fresnel began to challenge it, showing through interference and diffraction that light behaved as a wave. The discovery shocked the scientific world. If light was a wave, what was waving? Sound required air. Water waves required liquid. What medium carried light? The answer, scientists believed, must be the luminiferous ether, a mysterious, invisible substance that filled all of space, allowing light to ripple through it. For a time, this ether seemed to explain everything, until the coming of a mind that would remove the ether entirely and show that space itself carried the wave. Before that moment came, however, humanity still stood before three distinct realms of mystery: electricity, magnetism, and light. Each revealed glimpses of something greater, yet none provided the full picture. The electric spark, the magnetic pull, and the golden beam of sunlight all danced to the same unseen rhythm, but no one yet knew the tune. And so the first keynote, that these forces once seemed entirely separate, captures not just a scientific truth, but a reflection of how knowledge evolves. For thousands of years, humanity observed nature in fragments, dividing what was one into many, naming each wonder as if it existed alone. In the temple, the spark was divine; in the compass, the magnet was sacred; in the sky, the light was holy. It took centuries of observation, conflict, and imagination before anyone dared to believe that the same laws might govern them all. Each generation added a piece to the puzzle. Gilbert gave the world the term electricity. Franklin showed its kinship to lightning. Oersted and Ampere reunited it with magnetism. Faraday imagined its fields. And yet, even with all these breakthroughs, light remained the final piece, the most ancient and poetic of all. When we look back now, it is astonishing to realize how recent this understanding truly is. Less than 2 centuries ago, humanity still lived in a divided world of natural forces. The idea that light, that warm, eternal presence from the sun, was connected to the same energy that powered magnets and electric currents would have seemed fantastical. But nature had always known. The unity was there from the beginning, written in the structure of the universe. Humanity only needed a mind to read it. The mysterious forces of electricity, magnetism, and light once seemed entirely separate, and that separateness shaped human thought for millennia. It influenced religion, philosophy, and even art. Lightning was seen as punishment or divine power. The compass needle's movement was a symbol of fate or cosmic direction, and light itself was the language of creation. "Let there be light," the ancient texts declared, as if illumination were the first step toward understanding. But the beauty of science lies in its ability to transform mystery into meaning without diminishing the wonder. The first stage of that transformation began when humans dared to ask why. Why did the compass move? Why did amber attract? Why did light bend through glass or split into colors through a prism? Each question peeled away a layer of mystery, yet with each answer, new mysteries appeared. The separation of forces was not merely ignorance. It was the natural progression of discovery, where each phenomenon must first be studied in isolation before the connections can be seen. The forces of electricity, magnetism, and light were like three languages spoken by the same universe, yet humanity could only hear them one at a time. It would take generations before someone would translate them into a single, elegant conversation. But before that unity, there was wonder. There was the spark of curiosity, the flicker of the unknown, the magnetic pull of discovery itself. This was the age of awakening, an age when the invisible began to take form, when science slowly replaced superstition, and when humanity first realized that the world was not governed by chaos but by harmony. Electricity, magnetism, and light were the first notes of that harmony, mysterious, powerful, and destined to become one. Even as humans probed the natural world, the forces of electricity, magnetism, and light continued to challenge perception. By the mid-19th century, the stage was set for a revolutionary insight. The discoveries of earlier centuries had provided tantalizing glimpses. Currents could move needles, sparks could ignite phenomena, and light behaved both as particles and waves. Each observation deepened the mystery and heightened the desire for unity. Scientists now faced the monumental task of seeing these forces not as isolated curiosities, but as interconnected aspects of a single, universal law. It was during this period that James Clerk Maxwell entered the story. Born in 1831 in Scotland, Maxwell was a thinker unlike any other, a mind capable of synthesizing the abstract elegance of mathematics with the tangible world of physical phenomena. From an early age, he showed remarkable curiosity and insight, seeking patterns in everything around him, whether in the colors of nature, the movement of planets, or the invisible energies that seemed to flow through the ether. Maxwell did not merely observe the world, he sought to understand its hidden grammar, its rules and symmetries that governed phenomena previously considered unrelated. Maxwell's genius lay in his ability to take the fragmented discoveries of electricity and magnetism and weave them together into a cohesive framework. He began by examining the experimental work of Faraday. Faraday had introduced the concept of lines of force, an intuitive visualization of how magnets and currents influence space. Though lacking formal mathematics, Faraday's idea hinted at a deeper connection, that the forces surrounding electricity and magnetism were not isolated, but dynamic and pervasive, stretching across space. Maxwell transformed this qualitative insight into quantitative law. Using the precise language of mathematics, he described how electric and magnetic fields could interact, influence each other, and propagate through space as waves. These waves were the key to unification. Maxwell's equations demonstrated that variations in electric fields produce magnetic effects, and that changes in magnetic fields in turn generate electric effects. The equations predicted the existence of waves traveling through space at a fixed speed. Astonishingly, when Maxwell calculated this speed, it corresponded almost exactly to the speed of light, a revelation that would forever alter humanity's understanding of nature. Light, once thought to be an entirely separate phenomenon, was revealed as a manifestation of electromagnetic waves. Electricity, magnetism, and light were no longer three isolated forces but three facets of a single, elegant principle. The impact of this insight cannot be overstated. Maxwell had not only unified previously disparate forces, he had also revealed the underlying symmetry of the universe. Where human perception had once drawn boundaries, nature revealed none. The laws governing the flow of current in a wire and the oscillation of light through the ether were identical in essence. The same mathematical relationships governed both the spark and the sunlight, the magnet and the beam of laser light. In a single theoretical framework, Maxwell provided a language through which the universe could speak consistently, harmoniously, and predictably. Maxwell's discovery was more than an abstract triumph of intellect, it reshaped human understanding of reality itself. Imagine a world in which electricity, magnetism, and light were still perceived as unrelated forces. Communication would remain primitive, electricity would serve only limited local purposes, and the nature of light would remain a philosophical question rather than a technological tool. With Maxwell, the doors to modern civilization swung open. The concept of electromagnetic waves laid the foundation for radio, television, and eventually all wireless communication. The electric motor, the generator, the transformer. All these inventions found their theoretical justification in the equations that united the invisible forces of nature. Maxwell's insight also changed the way scientists approached the universe. No longer content with observing phenomena in isolation, researchers began searching for deeper symmetries and unifying principles. The idea that seemingly separate forces could be connected became a guiding philosophy, ultimately influencing the development of Einstein's theory of relativity and the broader quest for a unified understanding of physics. Every modern technological advancement, from satellites orbiting Earth to fiber, optic networks transmitting information across continents, carries Maxwell's intellectual legacy. The unity he discovered underlies both the practical and the philosophical. It is the principle that the world, no matter how complex it appears, obeys consistent laws that can be understood and applied. The journey from perceived separation to discovered unity was not immediate. Maxwell's work built on centuries of curiosity, experiment, and imagination. Early observations of electric sparks, magnetic needles, and beams of light were all steps toward a revelation that required patience, insight, and a unique blend of intuition and mathematical rigor. The story of these forces reflects the broader narrative of scientific progress. Observation sparks curiosity, curiosity inspires experiment, experiment generates patterns, patterns become laws, and laws eventually reveal hidden unity. Each discovery is a bridge from ignorance to understanding, each question a stepping stone to clarity. Moreover, the unification of electricity, magnetism, and light illustrates an essential truth about nature. Complexity often masks simplicity. To the casual observer, electric sparks crackle unpredictably, magnets pull with mysterious strength, and light dances in patterns both familiar and strange. Yet beneath this apparent chaos lies elegant order. Maxwell's equations exemplify this principle. The same concise formulas that describe a moving charge also explain the propagation of light through space. Nature's seeming multiplicity hides underlying simplicity, a lesson that extends far beyond physics to every realm of human inquiry. The historical context of Maxwell's work also underscores the interplay between culture, technology, and scientific insight. During the 19th century, the Industrial Revolution was transforming society. Steam engines powered factories, telegraphs transmitted information across continents, and chemical processes reshaped industry. Within this rapidly changing environment, the desire to understand and control natural forces was both practical and intellectual. Maxwell's unification of electricity, magnetism, and light was not merely an abstract academic exercise. It provided a conceptual framework that allowed society to harness energy in unprecedented ways. The equations that once seemed purely theoretical soon found applications in engineering, communication, and countless technologies that define modern life. Maxwell's achievement also demonstrates the importance of vision in science. While others measured, calculated, and observed, Maxwell could imagine the invisible fields themselves. The waves that carried energy across space, imperceptible to human senses yet fundamental to the workings of the universe. This combination of imagination and rigor, of creativity and precision, exemplifies the highest ideals of scientific endeavor. It shows that the pursuit of knowledge is not simply accumulation of facts, but the capacity to perceive connections that others cannot see, to unify what appears divided, and to articulate the hidden logic of the cosmos. As humanity continued to explore the implications of Maxwell's work, the unified vision of electricity, magnetism, and light led to further discoveries in optics, electromagnetism, and quantum theory. Scientists realized that electromagnetic waves exist across a spectrum, from long radio waves to invisible gamma rays, encompassing phenomena far beyond ordinary human perception. Light, in all its visible beauty, is merely a small slice of a vast spectrum of electromagnetic energy, each frequency obeying the same laws that Maxwell articulated. The separation of forces that had once seemed absolute was revealed as a limitation of perception, rather than a property of nature itself. Furthermore, Maxwell's work serves as a metaphor for the human journey toward understanding. It shows that apparent separateness is often temporary, a reflection of limited perspective. As knowledge advances, what was once divided and mysterious can become integrated and comprehensible. The forces of electricity, magnetism, and light, once considered unrelated, became a single, elegant system. A profound reminder that the universe operates according to principles that are discoverable, even if initially hidden. In reflecting on the historical journey from mystery to unity, one is struck by the courage and persistence of the thinkers who paved the way. Each generation contributed to a collective effort spanning centuries, a testament to the enduring human desire to comprehend the world. From the simple experiments of rubbing amber to the sophisticated mathematics of Maxwell, the story of these forces is a story of human curiosity, perseverance, and ingenuity. It reminds us that understanding is rarely instantaneous. It is the product of incremental insight, dialogue across generations, and the willingness to challenge assumptions. Even today, as technology surrounds us with devices powered by electricity and illuminated by light, the profound elegance of Maxwell's unification remains inspiring. Every electric current, every radio wave, every beam of sunlight is a living testament to the revelation that these forces are connected. The mysteries that once seemed insurmountable have been transformed into tools that empower human civilization. Yet the wonder remains. Despite our ability to manipulate these forces, their beauty, complexity, and subtlety continue to captivate. The spark, the magnet, the light, all remind us of the journey from ignorance to insight, from perceived separation to revealed unity. In this context, the first keynote, that electricity, magnetism, and light once seemed entirely separate, is not just a historical fact. It is a narrative of discovery, a meditation on the nature of knowledge, and a celebration of human curiosity. It illustrates how observation, imagination, and rigorous reasoning can transform mystery into understanding. It reminds us that the universe is both comprehensible and wondrous, that forces once perceived as separate are threads in a single tapestry, and that every insight is a step closer to the profound unity underlying all existence. As we conclude this exploration, the story of these forces invites reflection on the power of vision. Maxwell's work exemplifies how a single mind can perceive connections invisible to others, and in doing so, change the trajectory of science forever. The once divided forces of electricity, magnetism, and light now flow together in harmony, guiding our understanding and shaping the modern world. From this perspective, the mysterious separateness of these forces is no longer a limitation but a testament to the journey of discovery, a journey that continues even now as humanity seeks ever deeper insight into the elegant, interconnected universe that surrounds us. In the panorama of scientific discovery, there are figures whose minds transcend the ordinary, whose vision pierces the veil of nature's complexity and reveals truths hidden from the rest of humanity. Among these rare intellects stands a man whose insights would forever alter the course of physics, who would see what others could not, that electricity, magnetism, and light, once considered separate phenomena, were in fact deeply intertwined aspects of a single, elegant law. His name was James Clerk Maxwell, a Scottish physicist whose genius bridged intuition and mathematics, experiment and theory, imagination and logic. Maxwell's journey began in a world still divided by mystery. Electricity sparked unpredictably, magnetism pulled invisibly, and light flowed through space in waves or streams. The debates raged over its true nature. Scientists observed these forces, measured their effects, and devised experiments to quantify them, yet no one could see the underlying unity. Maxwell, however, was different. From an early age, he exhibited a mind capable of perceiving patterns that others missed, connecting dots across disciplines and synthesizing fragments of knowledge into comprehensive vision. Where others saw chaos, he glimpsed order. Where others saw isolation, he recognized relationships. Maxwell's approach combined two powerful qualities: a profound respect for empirical evidence and an extraordinary capacity for abstract thought. He immersed himself in the experimental results of Faraday, Ampere, and others, not merely to record what was observed, but to imagine what these observations implied about the universe at a deeper level. Faraday's notion of lines of force, which had seemed poetic and intuitive, became for Maxwell a canvas on which to paint the interactions of invisible fields. Through mathematics, he gave form to what had previously been an impression, a vision that could be communicated, tested, and built upon. The notion of fields, invisible regions of influence surrounding charges and magnets, was revolutionary. For centuries, forces had been thought to act only by direct contact or along lines that could be seen or measured. Maxwell's insight was to imagine that space itself could carry influence, that energy could propagate without a tangible medium, and that these fields could interact in a structured, predictable manner. It was a radical departure from conventional thought, requiring both courage and imagination to even contemplate. Maxwell's equations, developed over years of careful study and refinement, represented the culmination of this vision. They expressed mathematically the dynamic interplay between electric and magnetic fields. A current produces a magnetic field, a changing magnetic field induces an electric field. These interactions propagate through space as waves traveling at a constant speed. Each equation, precise and elegant, unveiled a truth about nature that had been hidden in plain sight. Maxwell did not simply describe phenomena, he revealed the underlying language of the universe. Perhaps the most astonishing insight was that light itself was one of these electromagnetic waves. The recognition that the same principles governing the motion of electric charges and the behavior of magnets could also explain the propagation of light was breathtaking. It unified three domains of physics that had been studied separately for centuries, revealing a hidden harmony that bound them together. The spark of electricity, the invisible pull of the magnet, and the radiant glow of light were no longer separate wonders, but expressions of the same universal principle. This unification was more than an intellectual exercise. It transformed how humanity could understand and interact with the natural world. By revealing that light, electricity, and magnetism were aspects of the same phenomenon, Maxwell laid the foundation for technologies that would reshape society. Radio waves, television, wireless communication, and countless other innovations owe their existence to his insight. The recognition of this unity was not just a theoretical triumph. It became the framework upon which the modern world would be built. Maxwell's vision was also deeply philosophical. It illustrated a profound principle that nature's apparent complexity often masks underlying simplicity. Forces that appear distinct to casual observation may, at a deeper level, be unified by a common law. This idea would echo through the centuries, influencing not only physics but the philosophy of science itself. Maxwell showed that by combining careful observation with imaginative reasoning, humanity could uncover hidden structures and principles, seeing unity where others perceived only separation. The personal journey of Maxwell himself is as remarkable as his scientific achievement. He was a man of curiosity and discipline, spending countless hours immersed in study, calculation, and reflection. He approached problems with patience, breaking them down into their essential components, and then reconstructing them with insight and creativity. Maxwell's notebooks reveal a mind constantly probing, questioning, and connecting ideas, searching not for immediate recognition, but for enduring understanding. His work exemplifies the principle that discovery is often a process of persistent insight rather than sudden revelation. The significance of Maxwell's unification extends far beyond his own time. His insight became a cornerstone for later scientific revolutions. Albert Einstein, for example, built on Maxwell's understanding of electromagnetic waves when developing the theory of relativity, showing that space and time themselves are intertwined in ways consistent with the behavior of light. Quantum mechanics, too, owes much to the conceptual groundwork laid by Maxwell's vision, as the study of electromagnetic interactions became central to understanding the behavior of subatomic particles. Maxwell's work thus bridges centuries, linking classical physics with modern scientific thought. One cannot overstate the courage it took to imagine the invisible. For centuries, science had been constrained by what could be observed and measured. Maxwell's genius was to trust that unseen structures, fields, forces, waves, had real existence, and that through careful reasoning, their behavior could be understood. This leap of imagination, grounded in empirical evidence, exemplifies the very essence of scientific insight. It demonstrates that vision in science is not mere speculation, but the ability to see what is hidden in the interplay of phenomena. Maxwell's unification of electricity, magnetism, and light also teaches a lesson about the cumulative nature of knowledge. He did not work in isolation. His achievements relied on the discoveries and observations of those who came before him. Faraday's experiments, Aristotle's observations, Ampère's formulations, all were pieces of a larger puzzle that Maxwell assembled into a coherent whole. This highlights an important principle. Scientific vision often emerges not from solitary genius alone, but from the dialogue between minds across generations, a cumulative process in which each discovery paves the way for the next. In examining the forces of electricity, magnetism, and light, Maxwell demonstrated that what appears mysterious and disconnected is often governed by deep, consistent laws. He revealed that nature possesses an underlying logic, a rhythm that can be expressed mathematically and understood conceptually. The unity he uncovered provides not only practical guidance for technology, but also profound insight into the nature of reality. It is a reminder that human curiosity, coupled with rigorous inquiry and imaginative reasoning, can uncover truths far beyond immediate perception. Maxwell's work also embodies the aesthetic dimension of scientific discovery. His equations are celebrated not only for their correctness, but for their elegance. They display symmetry, simplicity, and balance, qualities that suggest that the universe itself operates according to principles that are beautiful as well as functional. In this sense, the unification of electricity, magnetism, and light is a testament to the harmony underlying the cosmos, a harmony that can be discerned by the careful and insightful mind. Consider the technological implications of Maxwell's vision. The recognition that electromagnetic waves propagate through space led directly to the development of radio, television, and wireless communication. The principles he uncovered underpin every device that transmits or receives electromagnetic signals, from the simplest radio to sophisticated satellite systems. The ability to generate and manipulate electromagnetic fields forms the foundation of countless electrical technologies, from motors and generators to modern computing. Maxwell's work transformed abstract theory into practical application, showing that deep insight can reshape the material world. Yet even as we marvel at the applications, the human story remains central. Maxwell's journey reflects the courage to imagine what others cannot see, to follow intuition while remaining disciplined by evidence, and to pursue understanding even when immediate recognition is uncertain. His life illustrates that vision in science is not only about intellect, but about patience, persistence, and a willingness to explore the unseen. Through his work, he taught humanity to perceive unity in what once seemed fragmented, to recognize the connections that bind the universe together, and to apply that knowledge to create lasting impact. The unification of electricity, magnetism, and light also offers insight into the nature of discovery itself. It shows that understanding often emerges not from isolated observations, but from the synthesis of ideas, the ability to see patterns across domains, and the willingness to challenge conventional boundaries. Maxwell's genius was to integrate what others had studied separately, revealing the deeper order beneath apparent complexity. In doing so, he exemplified the power of vision, the ability to see connections hidden to all but the most perceptive minds. In reflecting on this period of scientific history, one is struck by the interplay of imagination and rigor. Maxwell's equations were not mere speculation, they were grounded in the careful study of experimental evidence. Yet they also required an extraordinary leap of imagination to conceptualize fields, waves, and invisible forces propagating through space. This combination of empirical grounding and creative insight defines the highest form of scientific vision. It reminds us that understanding the world requires both the precision of measurement and the freedom of imagination. Even today, the implications of Maxwell's unification resonate across science and technology. Every light that illuminates a room, every signal transmitted through the air, every device powered by electricity embodies the insight that these forces are interconnected. Maxwell's vision continues to guide researchers, engineers, and innovators, demonstrating that the hidden unity he uncovered is not only a theoretical principle, but a living, active force shaping our modern world. The story of Maxwell's discovery is also a testament to the value of persistence and dedication. Scientific insight often requires years of careful thought, meticulous experimentation, and relentless questioning. Maxwell's journey reminds us that breakthroughs are rarely instantaneous. They are the culmination of sustained effort, reflection, and the courage to explore what is not yet known. His vision emerged from decades of study, reflection, and synthesis, illustrating the disciplined patience required to uncover profound truths. Through his unification of electricity, magnetism, and light, Maxwell transformed human understanding of the natural world. He revealed the hidden order connecting forces once thought distinct, showing that the universe operates according to coherent, elegant laws. His vision continues to inspire, demonstrating that even the most complex phenomena can be understood when approached with insight, imagination, and rigor. In uncovering this hidden unity, Maxwell not only advanced science, but illuminated the path toward a deeper understanding of reality itself. The visionary insight of James Clerk Maxwell, which revealed the hidden unity of electricity, magnetism, and light, represents one of the most profound leaps in human understanding. His work illustrates not only the power of intellect, but also the synergy of observation, imagination, and mathematical reasoning. While the experimental contributions of Faraday, Arosted, and Ampere laid the groundwork, it was Maxwell who perceived the underlying structure connecting these phenomena, turning isolated observations into a coherent framework that reshaped both science and technology. Before Maxwell, the world of natural forces appeared compartmentalized. Electricity manifested in sparks and currents, magnetism in the mysterious pull of a compass needle, and light in the radiant glow from the sun or a candle. Each had its own set of experiments, laws, and traditions of inquiry. Observers could measure electric charge, study magnetic poles, or explore light's reflection and refraction, yet no one could articulate the connections between them. It required a mind capable of stepping back from the particulars and perceiving a pattern that spanned multiple domains, the kind of mind Maxwell possessed in extraordinary measure. Maxwell's genius was in abstraction and synthesis. He imagined space not as an empty void, but as a medium permeated by fields, regions of influence that could carry energy and propagate forces. These fields were not directly observable, yet Maxwell's reasoning allowed him to describe their behavior mathematically. He formulated equations that defined how electric and magnetic fields interact, how they evolve over time, and how disturbances in these fields propagate through space as waves. The brilliance of this approach was that it unified three forces, once considered independent, into a single coherent theory. The realization that light itself was an electromagnetic phenomenon was revolutionary. Light had long been studied as an independent entity. Newton had proposed a particle model, Huygens and Young explored wave behavior. Yet Maxwell's equations revealed that light is an electromagnetic wave traveling through space as oscillations of electric and magnetic fields. The speed of these waves, predicted purely from the equations, matched the measured speed of light. This elegant correspondence was far more than coincidence. It was a profound unification, demonstrating that electricity, magnetism, and light are different manifestations of the same natural law. This discovery transformed both theoretical physics and practical applications. Maxwell's theory provided the foundation for understanding the electromagnetic spectrum, encompassing not only visible light, but also radio waves, microwaves, X-rays, and gamma rays. It allowed scientists to comprehend phenomena far beyond human perception, revealing a continuum of energy propagation that underlies everything from natural light to wireless communication. The technological revolution that followed, telegraphy, radio, television, radar, and ultimately the Internet, traces its origins directly to Maxwell's unifying vision. Equally significant was the philosophical implication of Maxwell's work. By demonstrating the unity of forces, he challenged the notion that nature is inherently fragmented. What appears separate to the senses or even to detailed observation may, at a deeper level, be interconnected. Maxwell's insight exemplifies the principle that the universe often operates according to hidden symmetries and patterns. This notion influenced subsequent scientific revolutions, inspiring physicists to seek unifying principles in relativity, quantum mechanics, and beyond. It teaches that observation alone is insufficient. Understanding requires synthesis, insight, and the courage to see beyond the immediately visible. The personal dimension of Maxwell's work further illuminates the nature of scientific vision. He was a man deeply attuned to both mathematics and physical intuition. While many physicists excelled in one domain, Maxwell bridged them. He could interpret Faraday's qualitative notions of lines of force, render them mathematically, and predict phenomena that had not yet been observed. His notebooks show a mind constantly exploring connections, visualizing the invisible, and refining ideas until they coalesced into precise, predictive theory. Maxwell's intellectual journey demonstrates that the unification of knowledge requires both imaginative vision and disciplined rigor. Maxwell's vision also exemplifies the cumulative nature of scientific progress. His work did not emerge in isolation. It built upon centuries of observations and experimentation. The discoveries of earlier scientists provided the empirical foundation, while Maxwell's unique ability to abstract and unify allowed these pieces to form a coherent whole. This underscores a critical lesson. Groundbreaking insights often arise from the careful synthesis of prior knowledge, combined with the creativity to see relationships that others have overlooked. Science advances not only through discovery but through the unification of ideas. Furthermore, the practical implications of Maxwell's work cannot be overstated. By revealing the electromagnetic nature of light, he enabled the development of communication technologies that transform society. Radio waves, television signals, and cellular networks all rely on the principles he elucidated. Electric motors, generators, and countless devices harness electromagnetic interactions, converting theoretical insight into tangible power. In this sense, Maxwell's vision bridges the abstract and the concrete, showing how deep understanding can manifest in real-world transformation. Maxwell's approach to the unseen forces of nature also offers profound lessons about the role of imagination in science. Fields and waves, though invisible to the naked eye, became tangible through his equations. He trusted that the universe had structure and order even where direct observation was impossible. This combination of imagination grounded in empirical evidence is at the heart of scientific discovery. It demonstrates that the capacity to perceive unity among apparent chaos is as essential as technical skill or experimental expertise. The narrative of Maxwell's unification is also a story of persistence. Scientific breakthroughs rarely emerge overnight. Maxwell spent years refining his equations, reconciling discrepancies, and exploring the consequences of his ideas. His dedication exemplifies the patience required for deep insight. While flashes of intuition are essential, they must be coupled with careful analysis, rigorous reasoning, and relentless attention to detail. The hidden unity he uncovered was not immediately obvious. It required sustained engagement with both data and theory. Maxwell's vision reshaped the philosophical landscape of physics. By showing that electricity, magnetism, and light are unified, he illuminated the principle that the universe's forces are interconnected and governed by universal laws. This perspective inspired future generations of scientists to pursue unification on even grander scales, seeking common frameworks for the four fundamental forces, and ultimately influencing modern physics' quest for a theory of everything. Maxwell's work thus serves as both scientific foundation and philosophical beacon, illustrating that understanding is both attainable and profound. Consider the conceptual leap required to unify these forces. In Maxwell's era, electricity and magnetism were studied in laboratories, quantified through experiments, but largely treated as separate domains. Light was studied in optics, often in isolation from electromagnetic phenomena. To see these as expressions of the same principle demanded a rare combination of insight and courage. Maxwell's ability to make this conceptual leap exemplifies the power of visionary thinking, the capacity to perceive patterns beyond immediate observation, and to articulate them in a way that others can test, understand, and apply. Maxwell's equations, concise and elegant, encapsulate this visionary achievement. They describe how electric charges generate fields, how changing fields propagate as waves, and how these waves constitute light. The predictive power of these equations allowed scientists to explore phenomena previously unimagined. Wireless communication, electromagnetic radiation, and energy transfer across space all became not just theoretical possibilities, but practical realities. Maxwell's vision transformed abstract concepts into tools for understanding and controlling the natural world. Equally important is the aesthetic dimension of Maxwell's work. Scientists and mathematicians often remark on the beauty of his equations, their symmetry, elegance, and simplicity. This beauty reflects a deeper truth: the universe's underlying order is both functional and harmonious. Maxwell's unification reveals that nature operates according to coherent principles, and that understanding these principles allows humans to perceive the world not only accurately but beautifully. In this sense, scientific vision is inseparable from both intellect and wonder. Maxwell's unification also illustrates the interconnectedness of scientific discovery. His work demonstrates that no insight arises in isolation. It draws upon the observations, experiments, and theories of predecessors while simultaneously providing a foundation for future breakthroughs. In this continuum, individual vision intersects with collective knowledge, showing that science is both a personal and collaborative endeavor. Maxwell's achievement reminds us that even the most extraordinary breakthroughs emerge from a dialogue between imagination and evidence, past and present, theory and observation. The transformative nature of Maxwell's work is visible in the modern world. Every electric current, every wireless signal, every beam of light passing through fiber optic cables is governed by the principles he elucidated. Technology that shapes contemporary life, from communication networks to medical imaging, relies on the unity of forces he uncovered. Yet even as Maxwell's equations empower practical innovation, they also invite reflection on the underlying harmony of the universe, demonstrating that the natural world obeys principles far more elegant and interconnected than the senses alone can perceive. Maxwell's visionary insight continues to inspire not only physicists but thinkers across disciplines. It exemplifies how perception, imagination, and analytical reasoning can combine to uncover profound truths. The hidden unity he revealed reminds humanity that what appears fragmented may be interconnected, that complexity often conceals simplicity, and that understanding is possible through careful observation and synthesis. Maxwell's work transcends time, bridging centuries of inquiry and providing enduring guidance for scientific exploration. Moreover, Maxwell's unification underscores the importance of looking beyond the immediately observable. The invisible fields he described could not be seen directly, yet their effects could be measured and understood. This principle extends beyond physics in all domains. Patterns and connections often lie beneath the surface, waiting for the mind capable of perceiving them. Maxwell's vision is a reminder that insight requires both attention to detail and the ability to think abstractly, to see what is not yet obvious, and to imagine the unseen structures shaping reality. In reflecting on Maxwell's contribution, one recognizes the profound courage required to challenge conventional boundaries. Science in his time was largely empirical, grounded in observable phenomena. Maxwell introduced a conceptual framework that extended beyond immediate perception, positing invisible fields that could nonetheless be described mathematically and tested experimentally. His vision required the audacity to imagine the unseen and the rigor to substantiate that imagination through logical reasoning and precise formulation. Maxwell's insight also reveals the cumulative and iterative nature of scientific understanding. While his unification was groundbreaking, it relied on centuries of prior knowledge: Gilbert's observations of magnetism, Franklin's studies of electricity, Faraday's exploration of lines of force, and many others. Maxwell synthesized these contributions, providing a coherent theoretical structure that revealed the hidden unity. This narrative demonstrates that vision in science is both individual and collaborative, an interplay of inspiration, observation, and synthesis across generations. Finally, the unification of electricity, magnetism, and light exemplifies the transformative potential of visionary insight. Maxwell's work not only explained natural phenomena, but also enabled humanity to harness these forces in unprecedented ways. Modern communication, energy generation, and countless technologies trace their origins to his equations. Beyond practical impact, his vision reshaped humanity's conceptual understanding of nature, showing that seemingly separate forces are threads in a unified tapestry. In sum, James Clerk Maxwell's discovery of the hidden unity among electricity, magnetism, and light represents a monumental achievement in human thought. It is a testament to the power of vision, imagination, and rigorous reasoning. Through his work, he revealed the underlying coherence of the universe, transformed technology, and inspired generations of scientists to seek connections where others saw separation. Maxwell's insight endures as a guiding light, demonstrating that hidden unity can be revealed through patience, intellect, and the courage to see beyond what is immediately apparent. In the chronicles of human understanding, there are moments when observation and imagination converge to illuminate a truth so profound that it reshapes the very way we perceive reality. One such moment arose in the mid-19th century when James Clerk Maxwell, a Scottish physicist of extraordinary insight, formulated equations that revealed an astonishing connection. Light, the radiant phenomenon that had fascinated humans for millennia, was itself an electromagnetic wave. This revelation not only unified disparate forces but also transformed the foundations of physics, opening doors to realms of understanding and technology previously inconceivable. For centuries, light had been a source of wonder and mystery. It illuminated the world, guided human activity, and inspired both art and science. Ancient civilizations marveled at the sun's brilliance, the flicker of flames, and the subtle play of reflections on water. Philosophers and scientists alike sought to explain its nature. Was it composed of particles, as Isaac Newton proposed, or did it behave as a wave, as Huygens and later Young and Fresnel suggested? The debate was intense, reflecting the limits of perception and the challenges of interpreting phenomena invisible to the naked eye. Electricity and magnetism, by contrast, were studied in the context of interaction and motion. Sparks leapt between conductors, magnets attracted or repelled, and the relationship between charges and poles was painstakingly measured. Yet no one could see how these forces might relate to light, which seemed ethereal and separate from the tangible effects of currents and poles. For generations, these domains were isolated. Electricity and magnetism occupied the realm of the laboratory, while light belonged to the study of optics and natural philosophy. The path to unification required a mind capable of bridging the abstract and the concrete, a thinker able to perceive underlying patterns connecting what appeared separate. Maxwell possessed such a mind. He approached the problem not only with mathematics, but with profound intuition. He studied Faraday's observations of lines of force and the way electric currents could influence magnetic fields. He pondered the symmetry inherent in these interactions, imagining a dynamic, interconnected system in which energy could propagate through space. His work was both meticulous and visionary, blending empirical evidence with theoretical insight. Maxwell's equations described how electric fields change over time, how magnetic fields are generated by moving charges, and how these changing fields can induce each other. Through these interactions, disturbances propagate through space as waves. These waves, Maxwell calculated, travel at a specific speed, which, remarkably, matched the known speed of light. The conclusion was nothing short of revolutionary. Light itself is an electromagnetic wave, an oscillation of electric and magnetic fields moving in concert through the vacuum of space. This insight unified three domains, electricity, magnetism, and light, into a single, elegant framework. The implications of this discovery were profound and multifaceted. On a theoretical level, it provided a new understanding of the nature of light, resolving long-standing debates between particle and wave theories. Light was no longer a mysterious, isolated phenomenon. It was a tangible consequence of the laws governing electric and magnetic fields. On a practical level, this unification laid the foundation for technologies that would define the modern era. From radio and television to wireless communication and beyond, the recognition of light as an electromagnetic wave made possible the manipulation and transmission of energy across space. Maxwell's insight also exemplified the power of abstraction in scientific thought. While Faraday had imagined fields as lines of influence, Maxwell transformed this intuition into precise mathematical relationships. His equations provided a language in which the behavior of electric and magnetic forces could be predicted, quantified, and generalized. They revealed patterns invisible to the senses, showing that the oscillations constituting light obey the same principles that govern the interactions of charges and magnets. In doing so, Maxwell demonstrated that nature operates according to consistent, discoverable laws, and that phenomena once perceived as separate are in fact deeply interconnected. The unification of light with electromagnetic forces also transformed the conceptual landscape of physics. It suggested that the universe is not a collection of isolated phenomena, but a coherent system governed by universal principles. This perspective influenced generations of scientists, inspiring the search for further unifying theories. Albert Einstein, for example, would later build on Maxwell's framework in developing special relativity, recognizing the constancy of the speed of light as a fundamental aspect of space and time. Maxwell's insight thus bridged classical physics and modern theoretical frameworks, establishing a foundation upon which future breakthroughs could be built. Consider the elegance of the revelation. The very light that illuminates our world. The sunlight that warms, the glow of a candle, the brilliance of stars, is the manifestation of invisible forces propagating through space. Electricity and magnetism, previously studied in isolation, are inseparable from this radiant energy. The wave nature of light, once debated and uncertain, became a natural consequence of the laws of electromagnetism. Maxwell's equations rendered visible the invisible architecture of nature, revealing the hidden connections that govern the cosmos. The story of this unification is also a testament to the importance of vision in science. Maxwell's insight was not derived solely from measurement or observation. It emerged from the ability to imagine a world in which invisible fields could interact and propagate. He trusted that the universe has underlying order, and he sought to express that order in a precise, predictive form. This combination of imagination and rigor is a hallmark of scientific genius, demonstrating that discovery requires both the courage to think beyond the immediately observable and the discipline to verify those insights through calculation and experiment. Maxwell's revelation about light also illuminates the historical trajectory of human understanding. For centuries, philosophers and scientists debated the nature of light without the tools to unify it with other forces. Each observation, from Newton's prism experiments to Young's interference patterns, provided pieces of a puzzle that could not yet be completed. Maxwell synthesized these insights, connecting the dots across domains and revealing a deeper reality. His work illustrates how scientific understanding is cumulative, building upon prior knowledge while extending beyond it to uncover hidden truths. The practical consequences of recognizing light as an electromagnetic wave are immense. The electromagnetic spectrum, encompassing radio waves, microwaves, infrared visible light, ultraviolet X-rays, and gamma rays, is governed by the principles Maxwell elucidated. Technologies that rely on electromagnetic propagation, from radar to satellite communication, from fiber, optic networks to medical imaging, are all applications of the insight that light is part of this spectrum. Maxwell's equations, therefore, are not merely abstract formulations. They are blueprints for understanding and harnessing the energy that permeates the universe. Moreover, the unification highlights the symmetry and beauty inherent in nature. The oscillation of electric and magnetic fields, perpendicular to each other and to the direction of wave propagation, reflects an elegant structure underlying physical phenomena. Maxwell's insight revealed that what appears complex and multifaceted can often be expressed through simple, harmonious principles. This aesthetic dimension of his work underscores the interplay between intellectual clarity and the perception of beauty in scientific discovery. Maxwell's equations also exemplify the predictive power of theory. Before experimental verification, his mathematical framework implied the existence of electromagnetic waves propagating through space. Heinrich Hertz later confirmed these waves experimentally, demonstrating radio frequency radiation and validating Maxwell's theory. This interplay between theoretical prediction and empirical confirmation illustrates the dynamic relationship between thought and observation in science. Maxwell's vision anticipated phenomena that would only later be observed, highlighting the ability of insight to transcend immediate evidence. The discovery that light is an electromagnetic wave also transformed human perception of the cosmos. It suggested that the universe is filled with invisible energy, moving through space in predictable ways. Every star, every beam of sunlight, every artificial light source emits electromagnetic waves carrying energy across vast distances. This perspective expanded the human understanding of reality, revealing that what we perceive with our senses is only a fraction of the forces and energies at play. Maxwell's unification provided a framework for exploring these hidden aspects of the universe, setting the stage for both theoretical and technological advances. Maxwell's work also demonstrates the importance of interdisciplinary thinking. By integrating observations from optics, electricity, and magnetism, he transcended traditional boundaries between scientific fields. His ability to connect ideas across domains exemplifies the power of synthesis in discovery, showing that true insight often arises at the intersections of knowledge. The recognition that light is an electromagnetic wave is a product of this integrative vision, illustrating how breakthroughs can emerge from the convergence of multiple perspectives. Furthermore, Maxwell's unification of light with electromagnetic forces illustrates the profound interplay between simplicity and complexity in nature. While light, electricity, and magnetism manifest in myriad forms and behaviors, their underlying principles are elegant and consistent. Maxwell's equations capture this harmony, providing a concise mathematical description that governs phenomena ranging from the motion of electrons to the propagation of radio waves. The hidden simplicity underlying apparent complexity is a recurring theme in scientific discovery, and Maxwell's insight embodies this principle. The historical context of Maxwell's work further underscores its significance. In the 19th century, industrialization and technological progress were accelerating, yet the theoretical understanding of forces remained fragmented. Maxwell's unification provided a conceptual framework that could guide both scientific inquiry and practical application. By revealing that light is an electromagnetic wave, he enabled a deeper comprehension of energy, radiation, and the interaction of forces, insights that would influence both research and engineering for generations to come. Finally, the revelation that light is an electromagnetic wave emphasizes the transformative power of visionary thought. Maxwell's equations bridged the gap between phenomena previously regarded as separate, demonstrating that understanding often requires both imaginative intuition and rigorous reasoning. This insight reshaped physics, enabled new technologies, and expanded the human conception of reality. In illuminating the connection between light and electromagnetic forces, Maxwell revealed not only the nature of light itself but also the profound unity underlying the universe. Maxwell's revelation that light is an electromagnetic wave represents one of the most extraordinary intellectual achievements in the history of science. It unifies phenomena that had long been studied independently, offering a coherent framework that describes how energy propagates through space. This unification fundamentally changed humanity's understanding of the physical world and provided the foundation for countless technological innovations, from wireless communication to modern optics. Maxwell's work exemplifies the extraordinary interplay between imagination, mathematical rigor, and empirical evidence, a combination that defines the pinnacle of scientific achievement. Before Maxwell, the understanding of light was fragmented. Newton's corpuscular theory suggested that light consisted of tiny particles, while Huygens proposed a wave theory. Experiments in diffraction and interference revealed behavior consistent with waves, yet the relationship between light, electricity, and magnetism remained elusive. Electric currents were studied in isolated laboratory settings, magnetic fields observed in the motion of compass needles, and light analyzed separately in optics experiments. There was no unified theoretical framework to explain how these forces might be interconnected. Maxwell's genius was in seeing the underlying pattern. These seemingly distinct phenomena were manifestations of the same natural law. Maxwell's equations provided the mathematical structure needed to formalize this insight. They described how electric fields are generated by charges and how they change over time, how magnetic fields are generated by moving charges and currents, and how changing magnetic fields induce electric fields. Through these coupled relationships, disturbances propagate through space in the form of waves. By calculating the speed of these waves, Maxwell recognized a striking coincidence: it matched the measured speed of light. This identification transformed light from an isolated phenomenon into a natural consequence of electromagnetism. The consequences of this realization extend far beyond theory. Maxwell's unification of light with electromagnetic forces laid the groundwork for the electromagnetic spectrum. Human perception is limited to visible light, yet the spectrum includes radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays, all governed by the same principles. The practical applications of this knowledge are staggering. Radio and television broadcasting, radar, cellular communication, and satellite transmission all rely on electromagnetic wave propagation. Even medical imaging technologies, such as X-rays and MRI scans, depend on principles stemming from Maxwell's insight. By understanding that light is an electromagnetic wave, humanity unlocked the ability to harness energy in ways that were previously unimaginable. Maxwell's work also exemplifies the aesthetic dimension of scientific discovery. His equations are celebrated not only for their predictive power, but also for their elegance. The symmetry, simplicity, and harmony they display reflect the underlying order of nature. The perpendicular oscillation of electric and magnetic fields, moving in concert through space, illustrates a profound beauty, a complex phenomenon distilled into an elegant, predictive framework. This aesthetic dimension is not incidental, it reflects the coherence and logic inherent in the universe. Maxwell's insight allows humans to perceive this hidden order, demonstrating that understanding the world can be both intellectually rigorous and profoundly moving. The historical importance of Maxwell's work is also tied to the evolution of technology and society. By showing that light is an electromagnetic wave, he provided the theoretical underpinning for the development of wireless communication, beginning with Hertz's experimental validation of radio waves. This discovery eventually enabled radio, television, radar, and modern wireless networks, transforming human communication, commerce, and culture. Maxwell's equations offered a predictive framework, allowing engineers to design antennas, transmitters, and receivers capable of sending and receiving electromagnetic signals over vast distances. In this way, theoretical insight directly influenced the trajectory of technological innovation. Beyond practical applications, Maxwell's unification of light with electromagnetic forces has deep philosophical implications. It demonstrates that nature is fundamentally coherent, that seemingly separate forces are interconnected, and that the universe operates according to discoverable laws. Where humans once perceived distinct phenomena, sparks of electricity, the pull of a magnet, and the glow of light, Maxwell revealed an underlying unity. This perspective challenges the notion that the world is fragmentary, suggesting instead that complexity arises from the interplay of simple, elegant principles. The universe, in Maxwell's vision, is a harmonious system in which all phenomena are linked. Maxwell's work also highlights the interplay between empirical observation and theoretical insight. Faraday had visualized fields and lines of force, yet lacked the mathematical formalism to fully describe their interactions. Maxwell translated these qualitative ideas into precise equations, providing predictive power and conceptual clarity. This process illustrates a broader principle in science: observation alone is insufficient. Insight, abstraction, and rigorous formalization are essential to uncovering underlying truths. Maxwell's ability to synthesize observation and theory exemplifies the highest form of scientific reasoning. The implications of light as an electromagnetic wave extend to our understanding of the universe itself. All stars emit electromagnetic radiation across the spectrum, from radio waves to gamma rays. The light reaching Earth from distant galaxies is governed by Maxwell's principles, allowing astronomers to analyze its properties, determine distances, and understand the composition of celestial bodies. The unification of light with electromagnetism thus bridges terrestrial physics and cosmology, providing a framework for interpreting the universe on both small and large scales. Maxwell's insight also had a profound influence on subsequent theoretical developments. Albert Einstein's special theory of relativity, for example, is rooted in the constancy of the speed of light, a consequence of Maxwell's equations. The recognition that electromagnetic waves propagate at a fixed speed in a vacuum led to the realization that space and time are not absolute but relative, transforming physics and reshaping our understanding of reality. In this sense, Maxwell's unification of light with electromagnetic forces served as a foundation for one of the most significant revolutions in modern science. The practical realization of Maxwell's vision relied on experimental verification. Heinrich Hertz, in the late 19th century, generated and detected radio waves, demonstrating that electromagnetic waves indeed propagate through space as predicted. This empirical confirmation not only validated Maxwell's equations, but also paved the way for practical applications. From the first wireless transmissions to modern global communication networks, Maxwell's theoretical insight has been translated into tools that connect humanity, transmit knowledge, and enable technological progress. Maxwell's unification also underscores the importance of imagination in scientific discovery. The concept of fields and waves, invisible to the senses, required a leap of vision. Maxwell trusted that these unseen forces existed and that they obeyed consistent, describable laws. His work illustrates that scientific progress often depends on the ability to envision structures and relationships beyond immediate observation, and then to formalize these ideas rigorously. The discovery that light is an electromagnetic wave exemplifies the profound interplay between imagination, reasoning, and empirical grounding. The story of Maxwell and light is also a testament to the cumulative nature of science. While Maxwell synthesized the concepts into a unified theory, his work was built on centuries of observations and experimentation. From Newton to Faraday, each contribution provided essential pieces of the puzzle. Maxwell's genius lay in connecting these pieces, revealing a coherent picture where none had existed. This process illustrates the collective, iterative nature of scientific progress, where knowledge accumulates across generations, leading to breakthroughs that transform understanding. The identification of light as an electromagnetic wave also reshaped the philosophical understanding of the physical world. For centuries, humans perceived light as a mysterious, almost magical phenomenon, distinct from other forces. Maxwell's equations revealed that light obeys precise, predictable laws and is inseparable from electricity and magnetism. This unification embodies a fundamental principle: what appears complex or enigmatic is often governed by simple, elegant laws. By uncovering this hidden order, Maxwell illuminated not only the nature of light, but also the structure and harmony underlying all physical phenomena. Maxwell's work also highlights the predictive power of scientific theory. His equations implied the existence of electromagnetic waves across the spectrum, well before experimental detection. This capacity to anticipate phenomena illustrates a profound principle: deep understanding enables foresight. By revealing that light is an electromagnetic wave, Maxwell provided a framework for discovering and exploiting forms of energy invisible to the human eye, from radio waves to X-rays, demonstrating the transformative power of theory guided by insight and reason. The unification of light with electromagnetic forces also transformed human perception of reality. Visible light is but a tiny portion of the electromagnetic spectrum. Maxwell's insight revealed that the universe is filled with energy that cannot be seen directly, but is nonetheless real, measurable, and influential. Every signal transmitted through the air, every beam of light, every radio wave is governed by the same principles that Maxwell articulated. This perspective expands human understanding, showing that our senses capture only a fraction of the phenomena shaping the cosmos. Maxwell's discovery also demonstrates the interplay between simplicity and complexity. The oscillations of electric and magnetic fields may appear intricate, yet their behavior is governed by elegant equations. This duality, complex manifestation arising from simple principles, recurs throughout nature. Maxwell's equations provide a lens through which to perceive this harmony, allowing humans to understand and manipulate forces that were once mysterious. The recognition that light is an electromagnetic wave exemplifies the unifying simplicity that can underlay apparent complexity. Moreover, the technological and scientific legacy of Maxwell's insight continues to this day. Wireless networks, fiber optic communication, medical imaging, and radio astronomy all rely on the principles he established. The realization that light is an electromagnetic wave transformed not only theoretical physics, but also practical engineering, enabling a technological revolution that reshaped society. Maxwell's work serves as a reminder that visionary theoretical insight can have enduring and profound real-world impact. Finally, Maxwell's revelation that light is an electromagnetic wave highlights the transformative power of scientific vision. It illustrates how observation, imagination, and rigorous reasoning can uncover truths that redefine our understanding of the natural world. Maxwell's equations not only unified electricity, magnetism, and light, but also provided a framework for exploring the universe. Developing technology, and inspiring generations of scientists. The discovery embodies the essence of human curiosity, the drive to uncover hidden connections, reveal underlying order, and harness knowledge to transform both understanding and society. The story of scientific discovery is often one of pattern recognition, of seeing order where others perceive chaos. Among the most brilliant minds to navigate this path was James Clerk Maxwell, whose work revealed that electricity, magnetism, and light are not random or isolated phenomena, but expressions of universal principles that govern the natural world. Before Maxwell, these forces were studied independently, and their behaviors often seemed unpredictable, irregular, or mysterious. Electric currents sparked and flowed unpredictably, magnets pulled in invisible ways, and light appeared as a wave that defied easy explanation. Maxwell's genius was to perceive an underlying structure, an order that could be expressed mathematically and understood conceptually, showing that these forces obeyed elegant and universal laws. Maxwell's approach was as methodical as it was imaginative. He did not discard the empirical observations made by his predecessors. Instead, he built upon them. Faraday had introduced the concept of lines of force, visualizing the influence of electric and magnetic fields in space. Ampere had quantified the relationships between currents and magnetic effects. Maxwell synthesized these insights, applying rigorous mathematical frameworks to formalize what had previously been qualitative and intuitive ideas. In doing so, he demonstrated that nature's forces follow consistent, predictable relationships that can be expressed in concise, elegant equations. The elegance of Maxwell's laws lies not only in their mathematical form, but also in their ability to unify diverse phenomena. A changing electric field produces a magnetic field. A changing magnetic field produces an electric field. These interactions propagate through space as waves, which we perceive as light. By capturing these interdependent relationships, Maxwell revealed that the behaviors of electricity, magnetism, and light are not isolated accidents, but consequences of the same fundamental principles. In other words, the universe follows coherent rules, and the apparent complexity of natural forces is an expression of underlying simplicity. The universality of these laws was perhaps the most remarkable aspect of Maxwell's insight. The equations he developed are not confined to specific materials, environments, or scales. They apply everywhere in the physical world. Whether considering the glow of a candle, the transmission of radio waves across continents, or the radiation from distant stars, the same principles govern the behavior of electromagnetic forces. This universality underscores a profound truth. The laws of nature are consistent across space and time, reflecting an inherent order in the cosmos that human thought can apprehend. Maxwell's work also illustrates the power of theoretical abstraction in science. Before his equations, scientists could observe phenomena, record measurements, and note correlations, but the predictive power of these observations was limited. Maxwell's formulation allowed scientists to anticipate behavior, calculate effects, and predict new phenomena. His laws transformed observation into understanding, showing that the apparent randomness of natural forces is guided by precise, logical, and universal rules. Beyond its practical and theoretical significance, the elegance of Maxwell's laws carries philosophical and aesthetic weight. There is beauty in the symmetry of his equations, in the interplay of electric and magnetic fields, and in the revelation that complex behaviors arise from simple, consistent principles. This harmony reflects a deeper reality. Nature is not arbitrary. Patterns, regularity, and coherence underlie phenomena that might initially seem unpredictable or chaotic. Maxwell's insight invites both admiration and reflection, demonstrating that the universe operates according to principles that are discoverable, comprehensible, and elegant. The implications of understanding that forces obey universal laws extend far beyond physics. It influences technology, from the design of electrical circuits to the creation of wireless communication, and it informs human reasoning, reinforcing the idea that seemingly complex systems often have underlying structure. By demonstrating the elegance and universality of electromagnetic laws, Maxwell not only provided a foundation for practical innovation, but also offered a model for understanding the natural world itself. That observation, reasoning, and synthesis can uncover hidden order. Maxwell's insight was not simply an intellectual triumph. It reshaped humanity's conception of the universe. Where once forces seemed disconnected or mysterious, they now appeared as coherent expressions of deeper truths. The recognition that electricity, magnetism, and light follow elegant and universal laws marked a turning point in science, showing that the physical world is governed by principles that can be understood, quantified, and applied. This revelation inspired future generations of scientists to search for unifying principles in other domains, fueling the pursuit of knowledge that continues to this day. In summary, Maxwell's demonstration that these forces obey elegant and universal laws highlights the transformative power of insight grounded in observation and reasoning. His equations unified disparate phenomena, revealed hidden structures, and provided a framework for understanding both the natural world and the technologies derived from it. Through his work, humanity came to see that the universe is not a collection of isolated, chaotic events, but a harmonious system governed by laws of remarkable simplicity and universal applicability. This recognition stands as one of the most profound milestones in the history of science, illuminating the path toward both knowledge and discovery. The impact of James Clerk Maxwell's discoveries extends far beyond the realm of pure theory. It resonates through the very fabric of modern science and the technological world we inhabit today. Before Maxwell, electricity, magnetism, and light were studied as separate phenomena, each confined to its own experimental traditions and theoretical frameworks. Sparks leapt across wires, magnets influenced compass needles, and light illuminated the world. But these forces were seen as isolated, unrelated phenomena. Maxwell's genius was in demonstrating that they are interconnected, governed by universal principles, and capable of being expressed in precise mathematical terms. In doing so, he created a foundation upon which the edifice of modern physics and countless technological innovations would be built. Maxwell's theoretical framework revealed that electric and magnetic forces are inextricably linked, and that changes in one generate changes in the other. From this insight arose the realization that light itself is an electromagnetic wave, traveling through space at a speed determined by these interdependent forces. This unification was not merely an intellectual curiosity. It established a paradigm in which the behavior of natural phenomena could be predicted, quantified, and generalized. By providing a coherent description of electromagnetic interactions, Maxwell created the conceptual scaffolding for a scientific revolution that would unfold over the following century. The implications for modern physics are profound. Maxwell's equations served as a bridge between classical physics and the emerging ideas of the 20th century. Albert Einstein, inspired by the constancy of the speed of light predicted by Maxwell, formulated the special theory of relativity, reshaping humanity's understanding of space and time. The electromagnetic theory also anticipated phenomena later explored through quantum mechanics, including the quantization of energy and the wave-particle duality of light. In this sense, Maxwell's work is both foundational and prophetic. It not only explained observed phenomena, but also pointed toward deeper truths that would only be fully appreciated decades later. The technological consequences of Maxwell's insight are equally transformative. By demonstrating that electromagnetic waves propagate through space, he laid the groundwork for wireless communication. Heinrich Hertz would later experimentally verify these waves, leading directly to the development of radio. From radio signals to television broadcasts, radar systems, satellite communication, and the global networks that form the backbone of the Internet, every modern communication technology relies on principles first articulated by Maxwell. His work turned abstract theoretical insight into practical tools that reshape human society, enabling instantaneous global connectivity. Beyond communication, Maxwell's unification of electricity, magnetism, and light underpins countless modern technologies. Electric motors, Generators, transformers, and power grids all operate according to electromagnetic principles described by Maxwell's equations. The medical field benefits through MRI machines, X-ray imaging, and other diagnostic technologies reliant on controlled electromagnetic waves. Fiber optic communication, laser systems, and semiconductor devices all trace their conceptual origins to Maxwell's understanding of electromagnetic propagation. In short, the modern technological world, from energy production to global information systems, is a direct extension of the theoretical framework Maxwell established. Maxwell's work also transformed the methodology of physics. By combining rigorous mathematics with physical intuition, he demonstrated that abstract theory can predict phenomena that may not yet have been observed. This approach set a precedent for theoretical physics as a discipline, emphasizing the power of mathematical description in uncovering universal laws. Maxwell's vision illustrated that the behavior of the natural world, no matter how complex, can be distilled into elegant, predictive formulas, and that theory and experiment are complementary rather than separate pursuits. The influence of Maxwell's discoveries extends into cosmology and astronomy as well. Electromagnetic radiation is the primary medium through which we receive information from distant celestial objects. The light from stars, galaxies, and other cosmic sources travels across vast distances as electromagnetic waves, governed by the same principles Maxwell articulated. Understanding the universe, from the properties of cosmic microwave background radiation to the behavior of pulsars and quasars, relies fundamentally on electromagnetic theory. In this sense, Maxwell's work bridges the terrestrial and the cosmic, providing the foundation for exploring the farthest reaches of space. Philosophically, Maxwell's contributions illustrate a broader principle. The universe is coherent, predictable, and comprehensible. By revealing that diverse phenomena obey unified laws, he offered a vision of nature as an ordered system governed by principles that human intellect can discern. This perspective influenced not only physics but the philosophy of science, shaping the way generations of scientists approach inquiry, experiment, and the search for unifying theories. Maxwell's insight encouraged the pursuit of connections where others perceived disconnection, and the belief that even the most complex natural processes may be understood through careful observation, reasoning, and abstraction. The aesthetic quality of Maxwell's work also deserves recognition. The elegance, symmetry, and harmony of his equations reflect a universe that is structured, coherent, and comprehensible. Scientists often speak of the beauty inherent in the laws of nature, and Maxwell's equations exemplify this idea. They reveal that complexity arises not from randomness but from the interplay of simple, universal rules. This combination of utility and beauty is a hallmark of profound scientific insight. It demonstrates that understanding the universe is both an intellectual and an aesthetic achievement. Maxwell's unification also exemplifies the cumulative nature of scientific progress. While his work represents a monumental leap, it built upon centuries of observation and experimentation. The studies of Coulomb, Faraday, Ampère, and others provided the empirical foundation. Maxwell's genius lay in synthesizing these contributions into a coherent framework, revealing patterns that had remained hidden. His work illustrates that breakthroughs often arise not from isolated effort, but from the careful integration of prior knowledge with innovative thinking. Finally, Maxwell's contribution is enduring. Modern physics, from the principles of classical electromagnetism to quantum field theory, rests upon the foundation he laid. Engineering, communications, energy systems, and numerous technologies exploit the universal laws he discovered. Maxwell's work demonstrates that the pursuit of understanding the natural world can yield both profound intellectual insight and transformative practical impact. He exemplifies the scientist whose vision bridges theory and application, imagination and observation, revealing the hidden order of the universe and enabling humanity to harness its principles for progress. In summary, James Clerk Maxwell's work laid the foundation for modern physics and technology by unifying electricity, magnetism, and light under elegant, universal laws. His equations provided a predictive framework transforming both scientific thought and technological capability. From fundamental physics to global communication, from medical imaging to energy systems, the modern world reflects the power of Maxwell's insight. His vision endures as a cornerstone of science, a testament to the human capacity to perceive hidden order, articulate universal principles, and translate understanding into transformative innovation. The legacy of James Clerk Maxwell extends far beyond his own era, reaching across generations to inspire scientists, engineers, and thinkers to probe the hidden connections that govern the universe. Maxwell's vision revealed that electricity, magnetism, and light are not separate, unrelated phenomena, but expressions of universal principles obeying elegant laws. This unifying insight reshaped scientific thought, providing a framework that encouraged future researchers to seek coherence in what had previously seemed fragmented or chaotic. By demonstrating the interconnectedness of natural forces, Maxwell instilled in successive generations the belief that deeper structures lie beneath apparent complexity, waiting to be discovered by the observant and imaginative mind. Maxwell's equations exemplify this principle. They show that a changing electric field produces a magnetic field, a changing magnetic field induces an electric field, and disturbances propagate through space as waves, which we perceive as light. This revelation illustrates the profound unity underlying nature. Forces that appear distinct are in fact intertwined. Such insight challenges conventional thinking, inviting scientists to explore patterns and relationships that might initially remain invisible. Maxwell's vision thus became a guiding principle, a model of intellectual courage and conceptual audacity that inspired others to look beyond immediate phenomena and search for deeper laws of nature. The influence of Maxwell's work is evident in numerous scientific breakthroughs that followed. Albert Einstein, for example, drew directly on Maxwell's theoretical framework when developing special relativity. The constancy of the speed of light, predicted by Maxwell, provided a cornerstone for Einstein's revolutionary insight that space and time are relative rather than absolute. Similarly, quantum mechanics, the theory describing the behavior of matter at the smallest scales, emerged in part from questions raised by electromagnetic phenomena and light's wave-particle duality, both of which Maxwell's work had illuminated. In this sense, Maxwell did more than explain observed phenomena. He provided a conceptual lens through which future generations could reinterpret reality itself. Beyond physics, Maxwell's vision inspired a broader scientific mindset, the pursuit of unity, coherence, and underlying patterns. By showing that seemingly disparate forces could be described by a single set of laws, he encouraged scientists to approach the natural world with curiosity and a sense of connectedness. This philosophy has been central to countless discoveries, from the unification of fundamental forces in particle physics to the exploration of ecosystems in biology, where interrelated processes operate according to principles that may not be immediately obvious. Maxwell's insight demonstrates that the search for hidden connections is both a scientific strategy and a philosophical orientation. The ripple effect of Maxwell's work can also be seen in technological innovation. Understanding the unified behavior of electromagnetic forces enabled engineers and inventors to manipulate waves, fields, and energy with precision. Radio, television, radar, and wireless communication all emerged as practical applications of Maxwell's theoretical insight. Generations of scientists and engineers were inspired to explore the potential of electromagnetic phenomena, inventing devices and systems that transformed society. By linking theoretical insight with practical application, Maxwell set a precedent for scientific creativity. Curiosity about natural connections could lead not only to understanding, but to transformative impact on the world. Maxwell's vision also emphasized the importance of imagination and abstraction in science. While Faraday had visualized lines of force and observed patterns in electromagnetic interactions, Maxwell formalized these ideas mathematically. revealing relationships that were not directly observable. This act of abstraction demonstrated that understanding often requires thinking beyond immediate sensory evidence, trusting in patterns and principles that are invisible but real. Scientists inspired by Maxwell have continued this tradition, seeking hidden connections in fields ranging from cosmology to molecular biology, guided by the principle that nature's apparent complexity often conceals underlying unity. The influence of Maxwell's work is evident in contemporary explorations of the universe. Modern astrophysics, for example, relies on electromagnetic theory to interpret the radiation emitted by stars, galaxies, and other celestial objects. The electromagnetic spectrum provides insights into phenomena that cannot be seen with the naked eye, from radio emissions to X-rays and gamma rays. Without Maxwell's unifying vision, these interpretations would lack theoretical grounding. His work has inspired generations of astronomers and physicists to look for connections across scales, recognizing that forces and energies once thought separate are in fact interwoven threads in the cosmic tapestry. Maxwell's vision also embodies the notion that scientific understanding is cumulative and collaborative. His discoveries, built upon centuries of observation, experimentation, and theory, from Coulomb and Faraday to Ampere. In turn, his insights became the foundation for future breakthroughs, illustrating the iterative nature of science. Each generation of scientists has drawn inspiration from Maxwell's work, using it as a lens to uncover new relationships, develop technologies, and expand the horizons of knowledge. In this way, his vision transcends time, connecting the past, present, and future in an ongoing exploration of nature's hidden patterns. Philosophically, Maxwell's work encourages a perspective of interconnectedness and coherence in the natural world. By revealing that electricity, magnetism, and light obey unified laws, he challenged the idea that phenomena are inherently isolated or arbitrary. This perspective invites a deeper contemplation of the universe as a structured, harmonious system, where even seemingly random events may be linked to broader principles. Scientists inspired by Maxwell carry forward this worldview, seeking explanations that reveal underlying order, symmetry, and connection in nature. Education and mentorship have also been influenced by Maxwell's legacy. His work serves as an exemplar of how rigorous thinking, creative imagination, and disciplined analysis can combine to yield profound insights. Students and researchers studying his equations and theoretical approach learn not only about electromagnetic phenomena, but also about the methodology of scientific discovery itself. To observe carefully, reason systematically, and seek unifying principles. Maxwell's vision demonstrates that understanding the hidden connections in nature requires both technical skill and imaginative insight, a lesson that continues to guide aspiring scientists around the world. In summary, James Clerk Maxwell's vision has inspired generations of scientists to explore the universe's hidden connections. By unifying electricity, magnetism, and light under elegant and universal laws, he provided a conceptual framework that transformed physics, enabled technological innovation, and shaped scientific thinking for centuries. His work illustrates the power of insight to reveal the coherence underlying apparent complexity, encouraging scientists to seek relationships, patterns, and unity in all domains of inquiry. Maxwell's legacy is not only in the equations he wrote, but in the intellectual ethos he inspired: a commitment to curiosity, imagination, and the pursuit of understanding the hidden structures of the universe. The influence of James Clerk Maxwell endures in the present day, a testament to the timelessness of profound scientific insight. More than a century after his groundbreaking work, Maxwell's contributions continue to shape the frontiers of physics, technology, and the broader scientific endeavor. His unification of electricity, magnetism, and light did not merely solve the puzzles of his era, it created a framework that remains indispensable for contemporary research. Maxwell demonstrated that natural forces are interconnected, obey predictable laws, and can be described mathematically, principles that underpin virtually every modern exploration of the physical world. the elegance and universality of his equations continue to guide scientists in understanding phenomena that range from subatomic particles to distant galaxies. In the realm of theoretical physics, Maxwell's legacy is inseparable from the development of modern frameworks such as relativity and quantum mechanics. Albert Einstein, standing on the shoulders of Maxwell, recognized that the constancy of the speed of light, a direct consequence of Maxwell's equations, demanded a radical reconceptualization of space and time. The ripple effects extend further. Quantum electrodynamics, the most precise theory describing the interactions of light and matter, builds directly on Maxwell's work. Even today, researchers exploring high-energy physics, particle collisions, and the behavior of fundamental forces rely on the foundational understanding that electromagnetic interactions are governed by the universal laws Maxwell revealed. In this way, his vision continues to illuminate both the known and the unknown, guiding the pursuit of deeper truths about the universe. The technological impact of Maxwell's legacy is equally profound. Modern communication systems, including wireless networks, fiber, optic internet, and satellite technology, are all applications of principles that he first articulated. By demonstrating that electromagnetic waves propagate through space, Maxwell provided the conceptual tools necessary to develop radio, television, radar, and modern digital communication. Engineers and innovators continue to rely on the predictive power of Maxwell's equations to design antennas, signal processors, and communication protocols that connect billions of people globally. His work illustrates the enduring relevance of fundamental science. Insight into natural laws can drive technological revolutions that transform human society. Maxwell's influence is also evident in the exploration of the universe beyond Earth. Electromagnetic waves are the primary means by which astronomers observe distant stars, galaxies, and cosmic phenomena. Radio astronomy, for instance, allows scientists to detect signals emitted across the electromagnetic spectrum, revealing structures and processes invisible to the naked eye. Observations of cosmic microwave background radiation, the afterglow of the Big Bang, rely on electromagnetic theory to interpret the data and infer the universe's origins and evolution. Without Maxwell's unifying insight, the scientific understanding of the cosmos would be fragmented and incomplete. His work provides a bridge between terrestrial physics and the vast expanse of space, demonstrating that the same principles govern phenomena across scales. Beyond its scientific and technological implications, Maxwell's legacy continues to inspire a philosophical appreciation of nature's coherence and beauty. His equations exemplify the elegance that can arise from simplicity and universality, showing that complexity in the natural world is often governed by underlying order. Scientists today, whether working in physics, chemistry, biology, or cosmology, are guided by this principle that the search for hidden connections and unifying laws can reveal deep truths about reality. Maxwell's vision encourages an approach to science that combines rigorous analysis with creativity, fostering a mindset in which exploration and discovery are intertwined with the recognition of patterns and harmony. Education and pedagogy have also been profoundly shaped by Maxwell's contributions. Students studying physics encounter his equations as foundational knowledge, learning not only the specific laws of electromagnetism, but also the broader lesson that insight and imagination can reveal hidden order in nature. Maxwell exemplifies the synergy between observation, abstraction, and mathematical reasoning, demonstrating that scientific breakthroughs often emerge at the intersection of empirical evidence and conceptual clarity. His legacy endures in classrooms, laboratories, and research institutions worldwide, where his work continues to inspire curiosity, creativity, and intellectual rigor. Moreover, Maxwell's unification of electromagnetic phenomena serves as a model for interdisciplinary inquiry. By demonstrating that seemingly separate forces are interconnected, he encouraged scientists to look beyond narrow specializations and seek broader patterns. This perspective has influenced contemporary approaches to complex systems, including climate science, neural networks, and even socio-technical systems, where recognizing hidden connections is essential for understanding and innovation. Maxwell's work exemplifies the idea that the pursuit of fundamental understanding can resonate across disciplines, guiding inquiry in diverse fields. The legacy of Maxwell also emphasizes the importance of theoretical prediction in science. His equations anticipated the existence of electromagnetic waves long before experimental verification. Heinrich Hertz's experiments, which confirmed these waves, validated Maxwell's theoretical framework and demonstrated the predictive power of rigorous scientific reasoning. Today, this principle continues to guide cutting-edge research, from particle accelerators probing the smallest scales of matter to space telescopes observing the farthest reaches of the cosmos. Maxwell's approach, combining theoretical foresight with empirical testing, remains a cornerstone of scientific methodology. Furthermore, Maxwell's insight underscores the enduring relationship between fundamental science and societal advancement. Innovations in energy, communication, medicine, and transportation all draw on principles derived from his equations. Modern electronics, from smartphones to satellite networks, rely on electromagnetic theory to function. In this sense, Maxwell's legacy is not confined to the pages of scientific journals. It permeates daily life, shaping the ways humans interact, learn, and explore the world. The universality and applicability of his work demonstrate how foundational scientific understanding can yield transformative practical benefits. Maxwell's contributions also continue to inspire scientific imagination and ambition. Researchers today are exploring quantum information, photonics, and advanced materials, all of which rely on a deep understanding of electromagnetic interactions. Experiments in laser physics, superconductivity, and optical communication trace their conceptual roots to Maxwell's equations. By revealing the unity and predictability of electromagnetic forces, Maxwell provided a lens through which new phenomena could be envisioned, studied, and harnessed. His vision continues to guide the questions scientists ask and the methods they employ in pushing the boundaries of knowledge. In summary, James Clerk Maxwell's legacy continues to illuminate the frontiers of science today. His unification of electricity, magnetism, and light provided a conceptual foundation for modern physics, enabling the development of revolutionary technologies and guiding research across disciplines. Maxwell's work demonstrates the enduring power of insight, imagination, and rigorous reasoning in uncovering nature's hidden order. From theoretical physics to practical engineering, from cosmic exploration to everyday communication, the influence of his discoveries remains pervasive, inspiring scientists and innovators to explore, understand, and harness the universe's hidden connections. Maxwell's vision endures, a beacon illuminating the path toward knowledge, discovery, and the ongoing quest to comprehend the profound and elegant laws that govern reality.